Hello, welcome to Quadroli. My name is John, and in the previous video, we talked about asymptotic analysis, which is a useful mathematical technique for investigating the behavior of functions as their input approaches infinity. Asymptotic analysis gives essential insights on algorithm efficiency and performance. In this video, we can discuss on some general rules to help us determine the running time of an algorithm, and we'll do sample analysis using different master theorem. Before we start analyzing the algorithms, let's check some mathematical concepts and formulas that makes our analysis easy. Let's start with logarithms. Logarithms are inverse operations of exponential. Just like subtraction is the inverse operation of addition, or taking a square root is inverse operation of squaring. The four basic properties of algorithms are as listed in the left. Log xy to the base b will be equal to log x plus log y. Log x divided by y will be equal to log x minus log y, and log x raised to n equal to n log x. Similarly, log x to the base b can be represented as log x to the base a divided by log b to the base a. And there are other useful logarithm constants that we can see. Log 1 will always be 0, and log 2 to the base b will be equal to 1, and log b square to the base b will be equal to 2, and log b raised to x to the base b equal to x, and log b to the base a will be equal to 1 by log a to the base b. And there are some popular series towards the right: arithmetic series, geometric series, harmonic series, and also some approximations at the bottom. So let's now jump into some of the important guidelines for asymptotic analysis of code. So let's start with statements. So a statement is nothing but a line of code that does something. We consider a statement always executing some constant time Cn. We can add the constant time complexities of two or more statements. Let's say we have three consecutive statements. We add all the constant time complexities of each statement and get the total time complexity. Since we discard all the constants, most of the time complexity is calculated as O of 1. For example, var m is equal to 0. That is a constant time C1, and m equal to m plus 1 can be considered another constant time with C2. So the total complexity will become O of C1 plus O of C2. Since both of them are constant time, we approximate it and consider it as O of 1, which is a constant time complexity. A loop's execution time is the sum of the execution times of loop's statements multiplied by the number of iterations. For example, let's see this code. Var m is equal to 0. For var I equal to 0, I less than n, I plus plus, m equal to m plus 1. You can see here the loop runs for a whole input size n. So we can say it is linear, because as the input size increases, time taken for this loop to complete also increases. So total complexity is O of C1, which is of the top statement, plus O of C2 into n. C2 is the statement inside the for loop. So when we discard all the constant, we can say that the time complexity is O of n, which is linear time. So remember, the time complexities will be always an approximation. Now moving on to nested loops. Always the nested loops are analyzed from inside out. So when you want to find the time complexity of nested loop, always start from the statements inside the inner loop. We will start from m equal to m plus 1, which is always a constant time. So it will execute in constant time. And the inner for loop will run for n times, which is linear. So depending on the input size, it will run for n times. And also the outer loop runs for n times. So we can say total complexity is of C1, which is the outermost statement, plus O of C2 into n, which is equal to C into O of n square. We approximate it to quadratic time. So this loop will execute in quadratic time. By quadratic time, what we imply is that whenever the input size n increases, the time also increases quadratically. So that's what asymptotic analysis tells us. Now let's check the statements within loops. The best case of these statements within the loops will be the largest time complexity of the time complexities added. For example, in this code, you can see a single for loop and a nested for loop. So as you can see, the first for loop will run for n time, which is linear. And for the second nested loop, it will be always quadratic time, which is n square. So the deciding factor here is the n square. So this code runs in quadratic time. Now, if else statements. The worst case will be the largest time complexity of either the if or the else part. So as you can see, there is a single for loop inside the if statement, and for the else block, we are having a nested loop. So the complexity will be the largest time complexity, which is inside the else block. Even if the if condition is true, we will consider the else block as the deciding factor. So here deciding factor is the else block, and it has a quadratic time because that is a nested for loop and it runs for the full array dot length. So we can say the complexity of this if else block is determined by the else block, and it is in the order of n square, which is the quadratic time. And we also have logarithmic times. When an algorithm cuts the problem size by multiples of 2, we can say the algorithm is of log n. So here, as you can see, the I or the iterator value increases twice in the increasing sequence, and the iterator value j decreases by 2 in the decreasing sequence. For increasing sequence, the value of I doubles every iteration, and at any iteration k, we can say that 2 raised to k equal to n. So taking log on both sides, we can say log 2 raised to k equal to log n, which means that k into log 2 equal to log n, which means k equal to log n. So we can say that iteration happens in logarithmic times. Hence the complexity time is O of log n. So what does it mean? It means that the maximum iteration that will happen is where I equal to k. So when I equal to k, this loop exits and I reaches k in logarithmic times with respect to input. So that's how the complexity is calculated. So always look for how much time the loop executes. That will determine its complexity. Moving on, let's start with some code example. So in this code example 1, we can see we have a function sum, and inside it we have a while loop which runs for some time. Let's say it runs until sum is greater than now, and the iterator increments on every iteration, and the sum is increasing at the rate of iterator. What would be the complexity of such a function? So as we have learned, the first two statements will always run in a constant time, C1 and C2. And since we discard those constants, we can actually say it is not the deciding factor. Here, the deciding factor will be the while loop because the running time of the while loop determines the time complexity of this function. So let's see how the while loop runs and what is the rate of growth of this while loop with respect to the input now. So as we have already said, the while loop exits or terminates when sum is greater than num. And at every iteration, you can see sum equal to previous sum plus the iterator. But the iterator also increases before taking the sum for that particular iteration. If we closely observe each iteration, the sum is the addition of iterator with the previous sum. So we can say at any iteration, sum of I will be equal to sum of I minus 1 plus I. Here we know that this while loop determines the time complexity because it is the one which increases with respect to the input num. So As we know, this while loop exists when sum is greater than num. So when sum is greater than num, this while loop exists. For let's say kth iteration, the while loop exists. So the sum k will be equal to sum of previous k plus the current iterator. So current iterator always increases by plus 1. By visualizing this sum, we can say that sigma n equal to 1 to k n equal to 1 plus 2 plus etc. up to k, which is equal to k into k plus 1 by 2. So which will be equal to k square by 2 plus k by 2. Here k square will be the deciding factor because the rate of growth increases in quadratic time. So the time complexity is O of k square. How is this O of k square related to the n, which is the our input size? This O of k will determine the time complexity with respect to the input size n. So O of k will be equal to O of root n, taking root on both sides. So here since it is k square, when we take root on both sides, we will get O of k which is equal to O of root n. We will also do a few more code examples so that this concept is clear. So now moving on to code example 2, we have a function with a single for loop. And as you see, the loop ends when I into I greater than n. So the I increases in quadratic time. So the loop will execute up to k, where k is equal to I into I, where I is the iterator. As we saw in the previous example, here also the iterator increases in quadratic time. So O of I square will be equal to O of n, means time complexity with respect to the input size n will be equal to O square root of n. So it's similar to code example 1. Now moving on to code example 3, we have a function and we have a nested loop. So for nested loop, we have seen that we should start from the innermost loop. The innermost loop will execute up to k greater than n. As you can see, the k doubles every iteration, which means that it is in logarithmic times. And the second inner loop, whenever j plus n by 2 is greater than n, the for loop exits or terminates. So that for loop executes for n by 2 times at worst case. And for the outermost loop, it executes n by 2 times because it starts with I equal to n by 2 and ends with n. So calculating from inside loop, we will get O of log n, which is the innermost loop, into n by 2, which is the middle loop, and into n by 2, which is the outermost loop, means O of n square log n. So remember, for nested loop, always start from the innermost loop. And since we discard all the constant, we can remove the constant times occurred for count plus plus and the outermost count equal to 0. Moving on to code example 4. Here we have a function with nested for loop and we will start from the innermost loop. So the innermost loop will run until k is greater than n. Observe that the k increases in logarithmic times because k is multiplied by 2 in each iteration. The same is the case with the middle loop where j greater than n, the loop terminates and j is also incremented or multiplied by 2 for each iteration. So both of these two inner loops runs in logarithmic times. And for the outermost loop, since it starts with n by 2, we can say that it executes n by 2 times. So the total time complexity we can calculate as O of log n into n by 2, which means O of n into log n whole square. So moving on to code example 5. Here also we have a nested for loop, and we will start with inner for loop. Even though it seems like inner for loop runs for input size n, since there is a break statement inside the inner loop, it will always run once, and hence it can be considered as constant time. And the outer for loop will run for n times. So total complexity here would be c into n. Here c is the constant time that we considered for the inner for loop because of the break statement. So here the time complexity will be O of n, which is linear and which is provided by the outer for loop. Moving on to code example 6, we have a for loop as well as an if-else statement. So as we have learned, for if-else statement, the worst case will be the highest of either if block or the else block. Here the if block contains a statement, so it runs in constant time. But the else block is a loop which executes in n times. So the worst case will be the for loop inside the else and the outer for loop. So that means time complexity will be O of n into n, which means O of n square. You can apply whatever we have learned in this video to other code examples that you come across to find the time complexities of those code. That's it for this video. In the next video, we will talk about recursion and backtracking. See you in the next video, and thank you for watching. Bye.